if we start off then with chemical formula, and we'll work with butane to start with. Butane, but means 4 carbons. So the molecular formula, which is the number of atoms of each element in the molecule, is C4H10. So that's the molecular formula. Now that can be worked out if you actually draw out the displayed formula. The displayed formula gives all the atoms involved in the molecule and all the bonds. So remember that carbon can only have 4 bonds, and you can just build up the alkane and count the number of hydrogens. It agrees with that, the C4H10. In fact, alkanes have a general formula, which means you can work out for any number of carbons how many hydrogens there are, and it's CnH2n plus 2. There's also the empirical formula, which is the simple ratio of each element, the number of atoms of each element, the simplest ratio. So for C4H10 that would simplify to C2H5. Ooh, bit of a technical problem here. That's better. You also get the skeletal formula, which is very simple. The carbons are shown, well, the carbon to carbon single bond is shown by just a straight line, and you don't draw the hydrogens on. They're what they're known as implied. So there are hydrogens there, you just don't show them. If there are any other elements, you do show those. So for butane, it just looks a bit like that. And then there's the structural formula, which I find the most difficult to draw, I must admit. But I find it easiest actually drawing the displayed formula first, and then converting that to the structural formula. So the CH3 there and the displayed is that CH3 there, and the CH2, and then there's another CH2, and so on. If there are branches, then you put the branches in brackets. So for this compound here, we would have CH3, CH for the middle one, and CH3, and then CH3. But we must remember to put that branched one, that branch CH3, in brackets to show that it's branch and it's not part of the chain. So that methyl group there represented by the CH3 that's in brackets. Now we'll go on to isomerism. And the first thing we'll deal with is structural isomerism. Now, structural isomers have the same molecular formula. However, they have a different structural formula. The structural arrangement of the atoms is different. Now we'll work with butene, and here we've got but2ene, the double bonds on position 2, and it's C4H8, because the general formula for alkenes is CnH2n. And then we've got but1ene, which is also C4H8, so it has the same molecular formula. And there's another one there, methylpropene, C4H8 again. So all those 3 compounds are structural isomers. They have the same molecular formula, but they are different. They have a different structural formula. Now the other type of isomerism we need to deal with is ZE, or Z isomerism. And it's a type of stereoisomerism. And that means the structural formula will be the same. But they will have a different arrangement of the atoms. Now we'll work with but-2-ene again to show this. There's a but-2-ene structure. And if we do the structural formula, we'll see it's CH3, CH, CH, CH3. And then we've got another version of but-2-ene that looks like that. And that's CH3, CH, CH, CH3. The same structural formula. However, we call this one here the Z isomer, and we call this one here the E. E because their groups are on opposite sides, and the Z means they're on the same side of the double bond. Now, why do we get ZE isomerism? Well, you need two conditions, and these are important. The first is the CC bond, and that prevents rotation, so it fixes the groups in place. So that's the first reason. The CC double bond prevents rotation. Now there's the other condition as well, which means you must have two different groups on each carbon on the carbon-carbon double bond. Now I'll show you what you mean there. On this carbon here, for example, it's not shown in a skeletal formula, but there is a H there. So we have a H there and a methyl group on the other side, and a H there on a methyl group on the other side. Each carbon on the carbon-carbon double bond has two different groups. So those conditions are necessary to show ZE isomerism with the alkenes. Now if we can compare that with but-1-ene, where the double bond is on the position 1, you'll see there is the double bond, so that does prevent rotation of the groups. However, and a big but here, but there is not two different groups on each carbon. On that terminal carbon, there are two hydrogens. And so the condition is not met for ZE isomerism. So the but-1-ene does not exhibit ZE isomerism.